episode of Finno-Brick machining. We are dealing with this thing. This is, well, it's part of a wind turbine. It is the hub of the propeller. And, yeah, okay. So we don't do anything about with that one. But my neighbor has a problem with the blades of the propeller of being unbalanced, and they are not tracking correctly the same road, and furthermore they are out of balance in how they weigh. So yeah, okay. This one has 1 to 10 taper inside there. And what he needs now is a straight shaft with this taper in between. And then some means of, well, when you push that taper into the, it keeps there, but there should be something that locks it in place really. So, okay, let's do this. It's a late job actually, so late it is.
Going to drill 8.5 millimeter hole through the entire workpiece. So my first step here is to spot drill. So my next drill, which is 8.5 millimeters, will go straight into there. Please note that I did not face that surface. Well, later on this proves to be a big mistake. This is a long 8.5 millimeter drill. It is designed to cope with deep holes, but it is a good practice to have a starter hole with the same size drill, and when you drill with this one, then it goes straight. So yeah, so now I drill with this drill through the whole workpiece. This is a similar long drill, but this time it's 19 millimeters. And my mistake was not to face the surface, and furthermore this drill has a very bad tip. It starts to wobble a lot, and it squeals and makes all possible things. I still try to drill with it, but with the support from the side. But all it did was to drive my workpiece out of center line. So, oh man. So, I faced the end of the workpiece, and then I dialed it in again, because it really was driven to the side with a big drill. And furthermore, I bored the hole straight. up to 19 millimeters, so that when I push the drill there next time, it will not drive this workpiece to the side. Well, I still didn't look into the tip of this drill. Assumed it was good, but as it proved, the tip was really bad. It just didn't drill. It was just rubbing. I think somebody had tried to sharpen this drill, and not me. And it didn't work at all, so I needed to grind it, grind a better tip for that one. Oh. Okay, now, it proved that it worked really nice, and I got an equal chip from each of the flutes, and it was very easy going, just like a drill should be. And first it made a little bit strange sounds, but after it had been gone down maybe 10 millimeters, it started to make sounds that a drill normally makes. Now, this is 20 millimeter reamer. Pushing 20 millimeter reamer into a 19 millimeter hole is probably not the best practice. But what do I know? I'm just a hobby machinist, so yeah. And here I'm adjusting the speeds. It seemed like it squealed. Yes, it did, and now this is really a slow speed, and that's all too slow. So, finally I got it to the right speed, and then I pushed it all the way through. The only thing here was to clean the chips every now and then. The packings always have a habit to drop into the chip pan, and therefore I really try to catch them before they drop, and this time I was successful. Usually the last two ones drop into the chip pan. Now parting off a piece of this material. And this was the reason why I wanted to take away the packings and redial in this. Here I'm running with quite low speed and hand feeding it. but I will change it to automatic feed, power feed, and after that I will just well add the cutting fluid there. And well, at some point I noticed that my micrometer, my dial indicator stand is really a good thing to hold. You can use it like this. At some point I noticed that it will take forever to cut it with this speed, so well I increased the speed, and then I have this wood stick to catch the piece when it now parts off.
Okay, setting the compound angle here, and this is the calculations. The taper we need is 1 to 10. So, well, let me show you. So the angle, included angle is 5 degrees 43 minutes. Meaning 5.7 something, and half of that is about 2.8 degrees, 86 degrees. Sine from that is 0.0498. I made this calculation just to prove myself that actually it doesn't matter. It's so near 0.05. that in this case I cannot measure the difference between 5 and this 0.0498. I have a sine bar. So this is my sine bar. It's 100 millimeters long. And since I don't have cage blocks, so I use two of these. This is a parallel which is 14 millimeters at this side, and it's quite accurate actually. So I'm going to use it under there somewhere. And then this one I will put 5 millimeters more, which is 14 plus 5, it's 19 millimeters. So I dial into my I need these. I dial here like 19 millimeters. So that's actually 20, and then that's 19. So I put 19 in there, lock it in place. There you have 19 like that, and then I have an adjustable parallel like that, and then I just put it in between and make this thing. Well, this is too small. Let's take the next version. Okay. So now I should be able to adjust this to 14 millimeters. Quite easily actually. Yeah. I think there you are. Let's tighten it there like that, and then I actually measure it. It feels good. Yeah. So let's see now if this became 19 millimeters. Yeah, it is. Then I just put it under the other like that. Now what I want, okay, it's the wrong way around. I want it to be this way, because now I want this be adjusted this way. So it's easier for me to okay, let's see now. It's somewhere around 2 point something millimeters. Let's see. And then I just use this screw here. Well, it's not in a place. Okay, and then I try it from the other side as well. Seems to be there. Let's lock the answer here. And then I do a sanity check. Here I have this protractor, which is quite good. Let's see if I can I think that's our okay. So this is just a sanity check that we are on the correct planet here. So it's 2 point almost 3, and our goal was 2.86. So it's on the correct planet, at least. Okay, so probably my setup was correct. Now the next step here is to, this is precision ground 20 millimeter shaft, and my intention is to turn the taper into this part. This is now Loctited in place. It doesn't come out really, and then we have here a center which I have actually turned. It's not made. Originally it was made by a center drill, but then I turned it to be in an exact center. So now what we are going to do is to dial this in. Okay, and then we have to use backings in this case because this is hardened shaft, and it doesn't flex in the chuck. I mean, well, it bends, but it doesn't flex here. So I need to put some backing here to allow it to be adjusted from this end. Yeah, we don't want to bend this one. We want it to be straight. So I just put these backings here. This is okay. And now I want to have it in a really low gear in order to be able to turn it freely. Well, this is okay, let's see. That's in the center. That's also in the center. Why is it so? Yeah, it really wants to flex. Okay. Let's tighten it now a little bit more before I start dialing it in. So that's high, that's low. Okay, that's high. It's really low. Inside 1/100th of a millimeter at the moment. That's high. Low, high. Okay, that went, yeah. Okay. Oh yeah. Starts to be, now it's really, it's about the width of the needle at this place. So let's pull this out and see how it looks here. Well, it helped a lot to have the center there. The copper flexes so nicely that, okay, then I just tighten these properly. Oh yeah, it went down quite a lot. And now, okay, there you are. I believe it's, and now I just check the jaws that they really are tight, because next operation will be turning. Yeah, okay.
Now turning this material down to a diameter of 33 point, a little bit more, millimeters. And well, this material proved to be very easy to turn. Well, the only negative thing about this was the bird's nesting. I was not able to make the material I was not able to make it cut the chips. It made long stringy chips which yeah, formed these bird's nest every time I turned this around. And but nevertheless, after some turning, I was able to cut it quite easily down to 33 point maybe 2 millimeters. And furthermore, I had to monitor the temperature of this workpiece because at some point the Loctite would give up, and this is exactly what I didn't want to happen.
Okay, starting to make the taper now. It will be finished when I'm at this end. This is now 0.2 millimeter cut from the diameter, and let's see. So we are aiming so that we should be here 23 millimeters, and the other end should be something like 33. Let's see how this goes. I really don't know. I have to feed this by hand. Well, let's see now. Finishing cut, and I already feed it, tried to feed it a little bit slowly, but now I'm feeding it really slowly and only taking 0.2 millimeters from the surface. And well, let's see. And this is a tedious process. My laser did a reset. Oh yeah, this is okay now. Very decent. It feels smooth. Well, maybe a little bit lumpy. Okay, now I start it again. Sometimes when you have a lot of speed, the inertia will actually overdo the braking system in the VFD, and it will reset itself. So, okay, we get rid of these as well. Very nice. Oh, yeah, okay. Let's see if I can do something about the lumpiness. This should get rid of the high spots in there. Let's see how it looks and how it feels. Oh yeah, it made a difference. Still a little bit. Well, it looks amazing. And now let's give it the infamous beer tongue treatment. Well, it's beautiful. I like now how it looks, and the corners are not sharp. Yes. So we succeeded in this one. This is now the taper, and this is a 20 millimeter case hardened shaft, and it's really straight, and well, yeah, and this is how the taper looks. Very nice, and it also goes into there, knocks into place, and yeah, no wiggle or anything. It's quite accurate. So this can be used to balance, and now of course it doesn't come out. Oh, wait a minute. Yeah. Oh yeah. So this is now the taper, and then off the camera I made two of these. These are just rings with exact 20 millimeter inner diameter. It's a really good slip fit, and then you have group screws here. So group screws here, so you can tighten them into place. This just prevents the propeller from dropping down when you balance it. Actually, his intention is to put this on top of roller bearing. So I think it was Kate Fenner who made this rolling bearing system, which you can straighten your shafts. It's a similar system where you put the entire propeller on two bearings, and then it rotates freely, and you can adjust the balance, the weight of the wing of the blades, and also track that they are doing the same path. So for this reason, this had to be really accurate, and as you could see, I did turn this on. This is well, it's Loctited in place, and I turned it in that place so that it is the taper and the shaft are concentric. So, well, good for my neighbor. So, in the next episode of Finno Machining, I received the motor finally, so we can go on with rotating welding positioner. I will first of all make maybe some gears and the gearing system, how to well, put the power into that one. So, till next time, keep safe and see you!